Hi everybody, happy December. This is our last week of class. We're discussing, this is lecture 36, we're discussing section 5.4, the fundamental theorem of calculus, and also a topic called the average value of a function on an interval. Now, we actually discussed the fundamental theorem of calculus before break. And your recitation last Tuesday, recitation 13, had questions on it involving the evaluation theorem, which is this thing, and the fundamental theorem of calculus, which is this thing. And you had just basic questions on those. So the recitation for tomorrow is going to be more difficult questions involving the evaluation theorem and the fundamental theorem of calculus, and also a problem or two involving this other thing, the average value of a function on an interval. We'll have one more section to cover, section 5.5, which we'll discuss on Wednesday and Friday. Friday we do have a quiz, and so you won't have any recitation questions over section 5.5. So Wednesday in class we'll do recitation-like stuff. I'll actually give you a worksheet as if it were a recitation, and you'll do problems in your groups of two. And then the quiz on Friday involves those three sections, 5.3, 5.4, 5.5. Now it's going to have to be a basic question from 5.5 because we're only starting 5.5 on Wednesday, and then finishing 5.5 on Friday. So I'll give you a substitution question because I need to, because I want you to really do your best to keep up. And then our final exam is a week from Thursday. It's here in room 201 down the hall. So not in this room. What will be happening in this room is those of you who normally take your exams at the testing center, you'll be taking them in this room starting at 6. I'll be sending out an email about that. So the accommodated exams will start earlier. They'll start 6 p.m. on Thursday, and they'll be in this room. But everybody else will be down the hall in the big lecture hall. Now, if you would all please put away phones. I would like to not see phones, and I don't mean like temporarily set it down. I mean like put the phones away. All right. So the fundamental theorem of calculus, remember, is these two parts. Part one says if you build this wacky thing that's called an area function, we discussed this in class last Monday, and then you take the derivative of that area function, you get the original function back again. Another way of saying it is that this derivative kind of undoes the effect of this integration. It's the relationship between, I guess that's the way of saying it. That this derivative undoes the effect of this integration. And then fundamental theorem of calculus part 2 is this thing that's the relationship between definite integrals and indefinite integrals. Signed area and some calculation involving an indefinite integral, which is an antiderivative. So another way of thinking of fundamental theorem of calculus part 2 is that it's the relationship between definite integrals and antiderivatives. All right, so what I want to do, the first part of the meeting is stuff about fundamental theorem of calculus. So I want to do harder problems involving fundamental theorem of calculus. So example 1, It's going to be a two-part question. A, let g of x be this. So the definite integral from t equals 5 to t equals x of t minus t squared, that quantity to the 8th. All right? So this is not a harder problem. This is the exact kind of thing you did in recitation last Tuesday. So just write down what we, so I should have finished this up. Find g prime of x. That's the question. All right, so g prime of x just means we're going to be finding the derivative, d dx, of that baby. Well, now you realize that what we're looking at here is the left side of the fundamental theorem of calculus. So we're going to use the fundamental theorem of calculus, part 1, to say that this derivative is, you just simply pluck out the integrand and you change the variable to x. It's that easy. The only thing that's hard about this is knowing that it's that easy, that you don't do anything else. You don't find the derivative of this expression. You just pluck that expression out of that integrand. You pluck out the integrand and you change the variable. It's that easy. Okay, so example 2. Well, I want to do a little interlude here. If g of x equals this thing, well, actually, I'm gonna do a more general one. Here I've rewritten the fundamental theorem of calculus as an if-then, instead of just writing it as a single derivative expression. The derivative of this thing is this. So in other words, if you're going to think of this thing as your g of x, then your g prime is just f of x. Now I want to play with this. What if I do this? I change my variable to z. So what's g prime of z? Yeah, just f of z. And what if I get really crazy? Let's change the variable to y. If g of y is the integral from t equals a to t equals y, that's a function of the variable y. And so its derivative is a function of the variable y. You just pluck out the integrand. So it's all very straightforward, nothing fishy here. Now, watch this. I'm going to put parentheses around the place where the input goes. The variable in this expression is not t. The variable is the symbol y, which, you know, it's the variable y. So that parentheses there is the place where the variable sits. what do we call this sort of thing in this class? I've given this a name. Yeah.
In outside function?
Well,
at least in the context of the chain.
yeah, so, but when we were doing chain rule problems, we did this sort of thing, and I called this the empty version. So, this is the empty version of G. And what this is the empty version of G prime. It's no different from empty version stuff we did earlier in the semester. So question B. Let h of x be this. The integral from t equals 0 to t equals cos, t equals 5 to t equals cos x of t minus t squared, all raised to the 8th power. Find h prime of x. Well, the solution to this is h of x is actually g of cos x. In other words, it's if you take the empty version, the place where you would expect the variable to be, there's a whole function sitting in there. So in other words, h is a nested function. So in order to find h prime, I have to use the chain rule. I'm going to write the chain rule form. I have to do the outer prime of parentheses, and then inside those parentheses I have to put the original inner function. And then I have to do inner prime. So this is all really weird. And I was talking about this in my last class. I mean, this would be, like having to fly a plane at night, where you'd have to trust the instruments that you've learned to fly with. Like, you know how these instruments work, you know how these controls work, and one of the tests in flight training is, instrument training. Can you fly by instruments? You don't have the horizon to see because it's dark out. Well, so we have to trust that these tools that we've used will work. We have tools that work on these kinds of functions look weird. But you have to just trust your instruments. So we're going to have chain rule details. My inner function is cos x. It's the thing that's sitting where I would have hoped to just have a variable. Instead, somebody snuck in this whole function. And so I need my inner prime. We know that from back when we used to do the chain rule. So the derivative of cos x is minus sine x. Now here's where things get weird and wonderful. My outer function is an empty function. And it's this thing, but just empty. So the integral from t equals 5 to t equals empty parentheses of t minus t squared to the 8th. So again, that's the empty version. One of the reasons that I make you all put your phones away is that when I eventually do trip over this cable, which I'm certainly going to do, you won't have it on video. Okay, so this is the empty version. So we need to do outer prime. Well, if I've got one of these things as my empty version of my function, then my outer prime, my prime is just pluck out the integrand, and instead of having a variable, just have parentheses. So parentheses minus parentheses squared all to the 8th. So there's the empty version of the outer prime. So I have to assemble all these parts according to that prescription. So I do my outer prime, which is parentheses to the 8th, parentheses minus parentheses squared. Usually when we've done outer primes before, there's only one pair of parentheses to stuff the inner function into. Here there are two pairs of parentheses, but that's okay. I'm going to stuff both of these with cos x. And then I have to multiply by my inner prime. Minus sine x. All right, how'd I do? Remember, when I ask how'd I do, it's usually, yeah, I need parentheses. Need to multiply by the inner prime. So dot minus sign is a bad thing. And that's it. So again, you have to trust these tools. You have to know that I don't take the derivative of this x minus x squared all raised to the 8th power. I don't do that. I just pluck this integrand out of there and stuff it with something else, and then I do an inner prime. So again, this is just like flying by instrument. Okay, example 2. Let's do another one of these. Let g of x be integral as r goes from 0 to x of the cube root of 1 plus r to the 5th. Find g prime. Well, it's the exact same kind of thing. This is an easy problem. The only thing that's hard about it is knowing that it's easy, that all you do is you pluck out that integrand and you change the variable to x. Cube root of 1 plus x to the 5th. You don't take the derivative of this thing. You just pluck it out of there and you replace the variable r with the variable x. Okay. So that's question A. Question B is to let h of x be this thing. The same thing, but the upper limit is r equals x to the fourth instead of just r equals x. Find h prime. All right, well, so the first thing to start is to observe that h of x is g of x to the fourth. So in other words, h of x is a nested function. So h prime of x is going to require the chain rule. And I can't stress enough to write this form out. So then we just have to do the chain rule details over to the side. So my inner function is x to the fourth. That's a function of the variable x. So my inner prime is going to be also a function of the variable x. Inner prime of x is going to be 4x cubed. My outer function is the thing that's holding that. So the thing that's holding that inner function is those parentheses. The thing that's holding those parentheses is my outer function. So the integral from t equals, or r equals 0 to r equals parentheses of the cube root of 1 plus r to the fifth. So that's the empty version of the outer function. So my outer prime, again, the only thing hard here is knowing that it's not hard. You just pluck out the integrand, the cube root of 1 plus r to the fifth, and you change it from r to the fifth to just parentheses to the fifth. So we can assemble all these pieces then. We have to get my outer prime, which is the cube root of 1 plus parentheses to the fifth. And I have to stuff those parentheses with the original inner function, which is x to the fourth. It's the original inner function, but this doesn't look like the original expression at all. The original expression was that wacky thing with the integral. And then I have to multiply by inner prime, 4x cubed. Now I can clean this up. X to the fourth raised to the fifth power is x to the 20th. And I don't like to have things like this. I don't like to have a radical and then a dot and then some expression, because somebody reading this might think, oh, they didn't make the radical go far enough. Or maybe if you make the radical a little bit longer, they might mistakenly think that you meant for this thing to be inside. So I'm going to put that in front. 4x cubed times the cube root of 1 plus x to the 20th. That's it. So that's what I would call a more difficult problem involving the fundamental theorem of calculus, because you have to recognize that it's a chain rule question, and you have to a lot of stuff that we do in this class I describe as baby steps, just lots of baby steps. These are not baby steps. This is weird. This is a hard thing. The hard thing to know that it's this simple. And then the chain rule, that's never easy. So this is really cool. All right, meeting part 2 is about the average value of a function on an interval. Anybody watch the Bengals game on Thursday? You can thank me that they won, because I was watching it and they were getting their butt kicked, and then I stopped watching it. And so, meeting part 2 is average value of a function. Did Joe Burrow play the whole game?
Yeah.
Did he kind of perk up?
Yeah.
Or did his, yeah. Good old Joe. Anybody ever go to, what's it? The cafe in the Plains? You know, the place where he used to go for breakfast. I will email you in the middle of the night when it comes to me. If you had your phones out, which you don't, you could look it up, but you don't, so you can't. All right, so here's a geometric question. Given a function f that's continuous, on an interval AB, if we wanted to park a rectangle on that same interval, how high would that rectangle need to be? So how high would a rectangle sitting on that same interval AB need to be? How high would that rectangle need to be to enclose the same signed area? So we can draw a picture of this. Here's my A, here's my B, here's my f of x, and here's my signed area, which I've drawn as a positive thing. My graph is above the axis. But, you know, we're familiar with the idea that signed areas can be negative or they can be 0. And what we want to do is we want to park on that same interval a rectangle. And the signed area needs to be the same. And the question is, what is this height? Okay, so the strategy is for answering this question, is to first of all get the expressions for the signed areas. So I have an area on the left picture, and an area in the right picture. And then set those equal to each other. And then solve for h. So we're going to set them equal to each other. All right. Well, the area of the region on the left is this. Remember, that's the definite integral is this. That's the symbol for the signed area. Who can tell me what is the area of the region on the right?
H times B minus A.
Yeah, it's width, which is b minus a, times the height, which is h. So there, we've got the area, the expressions for the areas of each of those regions. We've set them equal to each other. So now we solve for h. We get h equals 1 over b minus a times this integral. Well, that thing, it wouldn't be calculus if we didn't have some sort of obnoxious new definition every day. So here we go. Here's today's new definition. So here are the words. The average value of f of x on the interval AB, or I'm just going to say the average value of f. Now, so these are some new words. I mean, you might think these are not new words, but the way that we're using these words is new. I'm sure you've used average before. So you know the average of my age and how old are you? 18. So the average of our age is 18 plus 110. So that's 128 divided by 2. So our average age is. The average of our ages is 64. We could average all of our ages. We could add up all of our ages and divide by how many people there are in this room. We'd get the average age of the people in this room. That's not what this is. So part of using a definition like this is realizing that this is something new. You see the words average used this way, and they don't mean what you thought of average meaning before. So there is a restriction on when you're even allowed to use these words. F has to be continuous on the interval AB. You don't get to use those words unless you have a function that's continuous on that interval. And here's the meaning. It's the number h. That's it. And so the geometric significance is that's the height that a rectangle would need to be on that interval to enclose the same signed area as the function on that interval. So h is the number, is the height that a rectangle on the interval AB would need to be in order to have the same signed area in order to enclose the same signed area as f of x on that same interval. And I think I won't say f of x, I'm just going to say f, because you can refer to the function by name. You can use whatever variable you want. You know, if I use t here, I would still get the number h. So there's the definition. So again, what I said before is when you see the word average used this way, part one of your job is to realize this is a new thing. It means this. So I'm going to do an example, and then I'm going to let you all do 2 examples. Find average value of f of x equals 1 over square root of x on the interval from 1 to 4. Okay. Well, first thing you need to know is, again, realize what you're being asked to find. These words are there. They mean this. So our calculation is going to be calculating h. So I'm going to start my solution by writing h equals. And then just, the right side of that expression. 1 over 4 minus 1 times the integral from x equals 1 to x equals 4 of 1 over square root of x. Now, I'm going to use, I've erased the fundamental theorem of calculus. This means that I'm going to do 1 over 3, and it's 1 over 4 minus 1 is 1 over 3. And what this means is I'm going to do the indefinite integral of 1 over square root of x, and then I'm going to evaluate from x equals 1 to x equals 4. So here, in going from here to here, I've used the fundamental theorem of calculus, that this definite integral is computed using this indefinite integral calculation. Now, this indefinite integral, I don't want to interrupt my flow here. So this indefinite integral, I'm going to do over on the side. I can't stress enough the importance of coming up with a style of presentation that's clear, that you don't equate things that are not equal and that you do equate things that are equal. Notice that things over here are numbers. This h is a number. But this thing is not a number. That's a function. I'm doing this dirty work off to the side. So I'm not going to put this, I'm going to do this dirty work and then go back and put the results back in there. Now this is the same as the integral of x to the minus 1/2. And so I can use the power rule for indefinite integrals or the power rule for antiderivatives. And this becomes x to the minus 1/2 plus 1 divided by minus 1/2 plus 1 And then I get a plus c because I have an indefinite integral. So that means the general antiderivative. So I use the power rule for antiderivatives. So that's x to the 1/2 over 1/2 plus c. All right, somebody raised their hand. How do I divide by 1/2? You're overworked. Oh, you just raised your hand. How do I divide by 1/2?
Multiply by 2.
Multiply by 2. Excellent. So this is 2x to the 1/2. In other words, 2 square root of x plus c. All of this does not need to be in that chain of calculations. I'm just going to bring all that back in and put it back here. So I'm going to have 1/3 parentheses 2 square root of x plus c, close parentheses, evaluated from x equals 1 to x equals 4. So again, I can't stress enough to segregate out work that can be done off to the side and don't put it in the main flow of your calculation. You want to make your calculations as clear as possible. Now I'm going to go on. Notice at the very beginning I started with h equals, and every one of those things in subsequent lines is still equal to h. Now I have to do the evaluation. Notice that I need to use parentheses because this 1/3 has to be multiplying the whole thing. That's crucial. So these outer parentheses, maybe I'll put a bracket around this. Also notice that the plus c cancels the minus c. Now remember, the evaluation theorem says there are two different ways of presenting it. One is go find any antiderivative and do this. This is capital F of b minus capital F of a. Another way of writing the evaluation theorem is what I did using the fact that this definite integral is equal to this calculation involving an indefinite integral. Well, if I do that version of the evaluation theorem, when I go get my indefinite integral and they mail it back to me, it gets mailed back with the plus c because it's an indefinite integral. So I'm not using a particular antiderivative, I'm using the general antiderivative, but that's okay because the plus c's get killed anyway. So this is 1/3 times 4 minus 2, so 1/3 of 2, so 2/3. I did this in all of its glory because I wanted to come back and illustrate this. My original function is f of x is 1 over square root of x, and it looks something like this. It goes through 1, 1, because square root of 1 is 1, so 1 over square root of 1 is 1. And it goes through 4, comma 1/2, because 1 over square root of 4 is 1 over 2 is 1/2. And so we're talking about this signed area, and that signed area is the number 2. And then what we found out is, and this goes from 1 to 4. What we found out is if I park on that same interval from 1 to 4, a rectangle, and it has height two-thirds, there's my answer. My height is the number 2/3. What we found out is that this signed area would also be the number 2. But the answer was, what's h? What's the average value of the function? It's that number 2/3. And that's just an illustration of the significance of it. All right, so we have 8 minutes left. Let me give you 2 problems to do. If you would please scoot up next to somebody. So if you're sitting by yourself, maybe move down and sit next to somebody, or move over. So the first example is, a bunch of you haven't moved. Let's see, maybe you could go sit with Chris. Could you relocate, or Chris, could you relocate? I want everybody, and then can you maybe come down? Yeah, maybe just go up. Just scoot over here. Make a group of 3 here. Thanks. Find the average value of the cube root of x on the interval 1, 8. And then question 2. I think I'll leave question 2 for you to do at home. You're going to, like I said at the start of the hour, you're going to have questions like this in recitation tomorrow. So example 3 is find the average value of f of x equals cosine of x on the interval (0 to pi over 2). All right. Gabriel, you could pause that, and I'm going to stop talking and let you all work on that first problem. First of all, notice this is the graph of y equals x to the 1/3. It's the graph of y equals x cubed, but with x and y interchanged. And so we're considering this signed area from 1 to 8, and we're wondering how high that rectangle would need to be on the same interval to enclose the same area. So the solution to this is, write down h, which is going to be 1 over 8 minus 1 times the integral from x equals 1 to x equals 8 of x to the 1/3. So that's going to be 1/7. And then I'm going to go ahead and use the power rule right away. X to the 1/3 plus 1 divided by 1/3 plus 1. And then I have to evaluate that from x equals 1 to x equals 8. So there's a particular antiderivative. So that's going to be 1/7 times x to the 4/3 divided by 4/3, evaluated from x equals 1 to x equals 8. Now notice, I'm going to get as much mileage out of this as I can by simplifying before I do the evaluation. Now, dividing by 4/3 is the same as multiplying by 3/4. So I'm doing 1/7 times 3/4, x to the 4/3, evaluated from 1 to 8. I'm going to pluck out the 3/4. So 1/7 times 3/4, because I don't need to drag that around. So I'm going to have x, just x to the 4/3, evaluated from x equals 1 to x equals 8. So that's 3 over 28. And then it's going to be 8 to the 4/3 minus 1 to the 4/3. Anybody know what 8 to the 4/3 is? Good answer. No. This is one of those things where you might think you need your calculator or your phone. But if you had your phone, I would have just let you use it to figure out what the name of that restaurant is. I wouldn't let you use it for this. Remember that 8 to the 4/3 is 8 to the 1/3 times 4, but that means 8 to the 1/3 raised to the 4th power. Oh, but 8 to the 1/3, that's just 2. 2 to the 4th, that's just the number 16. So this is something that you can, oh, did you get that? Woo! All right, you can collect your cash prize later. All right, so this is going to be 3 over 28 times 16 minus 1. So 3 over 28 times 15. So that's, oh, did I erase my graph? Dang it. All right. So 45 over 28. That's how high that rectangle needs to be. We're done. Thank you all.